Hello dear friends, welcome my channels. Today's discussions is based on group theory and topology. So first problem is GATE 2012. So let Z cross Z, let Z cross Z R equals to Z cross Z and I equals to Z cross 0. Then which of the following statement is correct? I is a maximal ideal but not prime ideal of R. I is a prime ideal but not maximal ideal of R. I is both ideal as well as a prime ideal of R. I is neither maximal ideal nor a prime ideal. So friends, if R equals to R1 cross R2 cross R3 and dot 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 cross Rn and I equals to I1 cross I2 cross I3 cross dot 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 I cross In, then R by I, R divided by I equals to isomorphic to Z by Z cross Z by Z cross Z by 0. So it is isomorphic to Z. Since Z is an integral domain, so that I is prime ideal not maximal. So friends, I is a prime ideal but not maximal. Number B is correct. Next problem friends. The number of elements of conjugacy class of the 3 cycle 2, 3, 4 and in the symmetric group is 20, 40, 120, 216. So friends, 2, 3, 4 can be written this way: 1, 2, 3, 4, 5 and 6. This way it can be written. So the number of conjugacy class of the 3 cycle is 6 factorial. It can be written 6 factorial divided by 3 to the power 1 divided by 1 factorial and 1 to the power 3 divided by 3 factorial. It can be written this way, and this value is 6 factorial divided by 3 into 3 factorial. 3 into 3 factorial. So this value is 6, 5, 4 divided by 3 equals to 40. So answer B is correct. Next problem is the number of element of the principal ideal domain can be. So friends, if we will find out the number of domain, so it can be written p to the power n. So friends, p to the power n equals to order of principal ideal domain. Principal ideal domain should be written p to the power n. In here only possible 25, because 25 is equal to 5 square where 5 is prime, and here p is prime. Now friends, again we start GATE 2008. G is equal to R by 0, H is equal to minus 1, 1. Phi such that G tends to H defined as phi x is equal to x divided by x bar. So it is homomorphism. 1, 1. So friends, whatever you see, phi x can be written x by mod x. So it can be written this way: 1, minus 1 when x greater than 0 and when x less than 0. So I draw a diagram, and this is the phi, and this is the domain, and this is codomain. So friends, we see that G is equal to R by 0 and H equals to -1, 1. So whatever we see onto homomorphism phi such that G tends to H are onto homomorphism, but not 1 1, but not 1 1 1. So answer is C, and onto homomorphism which is not 1 1. Let's solve, friends, another problem. GATE 2006. So friends, in the GATE 2006, you see that let M3, R be a ring, 3 cross 3 ring real matrix, and I, J, M3R are defined as A, B, C. This way and this way can be defined. So we have X, Y, Z, U, V, W, and R, S, T into A, B, C, 0 0 0 0 0 0. So this is M3R. This point. This is called I. So if I will multiply, then I get AX plus this way multiply. So whatever AX plus Y0 plus 0, and another is AU into AR matrix multiplications, and BX, BV, and BR, and CZ, CU, sorry, it is BU, CU into CR, which is does not equals to sorry, it is which is does not equals to I. Similarly, when multiplication is A, B, C, 0 0 0 0 0 0, and X, Y, Z, U, V, W, R, S, T, when I multiply, then we see that the value is AX, A, Y, AZ, 0 0 0 0 0 0. This portion it belongs to I. So it is I is right ideal. I is right ideal. I is right ideal. So my possibility, this is I is right ideal, J is left ideal. No, this point, this and this two option is correct. Maybe correct, not correct. So again I will check in case of J. So J is ABC 0 0 0 0 0 with multiplied x y z u v w r s t. Then whatever I get, friends, I get this value, same value I get ax ay az bx by. Just multiply this way, this is the multiplication method. So ax bx c cx. Similarly, when I multiply this way, then ay by cy and az bz and cz, that does not equals to j. This is j portion. So another way we can multiply j is, similarly we can see that j is left ideal. So how j is left ideal, friends? Very simple. Just multiply x y z u v w r s t with abc 0 0 0 0 0 0 0. So whatever you get first column is ax plus by plus cz, ax plus by plus cz, and mid portion is 0 and second portion also 0, and third is eu plus bv plus cw, another portion is 0 0, and second is ar plus bs s plus ct 0 0 0. So j is left ideal, friends. So which option is correct? I is my first option is correct. So j is left ideal. I hope then it is everyone can understand what is left and right. Again, the question is GATE 2005. Let D8 denote the symmetry of the squares. The minimal number of generator for D8 is. So minimal number of generators for D8 is 2, because D8 is the group of symmetrics of a square dihedral group. Next, friends, we are going to topology problem. We are going to solve topology problem. GATE 2004. GATE 2004 topology problem. In R with usual topology, the set U equals to x belongs to R, and minus 1 to 1 less than equals to 1, less than equals to x less than equals to 1, x does not equals to 0 is neither Hausdorff nor first countable, Hausdorff but not first countable, first countable but not Hausdorff, both Hausdorff and first countable. So friends, how can I solve this problem? You see that u is equal to x belongs to R such that minus 1 less than equals to x less than equals to 1, and x does not equals to 0. So minus 1 by here, minus 1 by z does not equals to 1 by z, but 1 by z and minus 1 by z both belongs to u. So minus 1 by z minus 1 by z belongs to minus 1 comma 0, and 1 by z belongs to 0 comma 1, and minus 1 comma 0, minus 1 comma 0 and 0 comma 1 are disjoint set, are disjoint set. Hence u is Hausdorff and first countable. Hence u is Hausdorff and first countable. So first countable, both Hausdorff and first countable, option D is correct. Next friends, next question is very conceptual. A matrix space is always first countable, friends. A matrix space is always first countable. So every matrix space is first countable. A topological space, a topological space is first countable, is first countable a topological space is first countable if for each a countable set of open sets, for each set of open sets containing exist with each open set containing contains a point that is first countable if and only if at every point a countable local base exists. If at every point a countable local base exists. So friends, matrix space is always, and you can get always a countable local base exists in case of matrix space. So it is first countable space. Number 2. Let x comma d be a matrix space. Let a subset x and x belongs to x, and d x comma s is infimum of x comma a and a belongs to a. If d x a equals to 0 for all x belongs to x, then which of the following must be true? So friends, this problem is coming from CSIR net examinations. So friends, you have to remember one result. Which result? If dx comma a equals to 0, then x belongs to a bar, a dense set. So friends, this is the given that dx comma a equals to 0, so x belongs to a bar. Here x comma d is a matrix space, x comma d is a metric. X comma d is a metric space and distance of point from a set. Dx comma a distance of point from a set. Then dx comma a equals to 0 is x belongs to a bar x tends then set. So friends, whatever we see that x is the subset of a bar and reverse contradictions and reverse for formula, and x means vice versa. X belongs to, that is x belongs to a bar, then dx equals to a equals to 0 and x, so vice versa. So whatever we see a is dense in x. This answer is correct. Again we are going to solve another problem. CSR net 2012. Let x be a metric space and a subset of x, proper subset of x, be a connected set with at least two distinct points. Then the number of distinct points in a is, how can I find out the number of distinct points? X equals to metric and a subset of x where a is connected and a is subset of connected and mod of a, and this is also given that at least two distinct points. So mod of a, order of a greater than equals to 2. So whatever this example, I choose a example that r is my x, r is equal to x and a, r is a, x is equal to r and a at least two element exist. So this 2 point a, suppose b, this 2 point exist in a. So the possible is only for when a is uncountable. When n is uncountable, then it is possible, because equals to 2 is not possible, because singleton set is not possible. Singleton set x is not possible because a singleton set is only connected, only one singleton set is only one possible connected, but here 2 point exist, so both are connected. Connected means you cannot get any disjoint sets. Again the problem is, consider the space S equals to alpha comma beta belongs to Q, subset of R square, and where Q is the set of rational numbers, then SC is the connected in R square, SC is connected in R square, S is closed in R square, SC is closed in R square. So friends, here S equals to D cross D, proper subset of R square, and SC equals to RC, R complement R square minus S, and R square minus S is, note that S is countable, equals to R square minus countable space, countable, because S is alpha beta by beta belongs to Q. This portion is countable set. So equals to path connected, equals to path connected. So path connected. So path connected equals to ted equals to connect. That implies connected. This logic is very important, that r square minus countable equals to path connected. Path connected equals to connected. So friends, whatever we get, SC is connected in r square. So friends, SC is connected in r square. So this result is very important. This is very important result. And next, so friends, which of the following is matrix on R? dxy comma mean xy dxy comma x mod of x minus a minus y, this is correct. And dxy into x square y square, this is also wrong because this is quadratic. If I draw, then x minus y, this is the positive way, this portion is linear, and x cube minus y cube, this is also correct. But d equals to dxy mean xy, it is not correct. Because how? Because if I choose d minus 1 comma minus 3, then whatever I get mean of minus 1 comma minus 3, and that equals to minus 3, which is less than 0. But matrix space is always positive, so contradict with positivity. So friends, similarly you can see that x square minus y square, this is also not possible, because d of minus 1 whole square minus 1 whole square equal 1 whole square plus 1 whole square equal to 0, but minus 1 does not equals to 1. So these 2 points are not matrix space. Matrix space is only these two. Next friends, next problem is, let x be a topological space and u be a proper dense open subset of x. Pick the correct statement of the following. If x is connected, then u is connected. If x is compact, then u is compact. So friends, x is connected, then u is connected. So what is the meaning of the connected? Connected means bounded. It should be bounded plus closed equals to compact. What is the meaning of the compact? And u be a proper dense, must remember open subset of x. Compact, it is the remembering point. U subset of x, and x is a topological space, any topological space, such as x is R is unbounded, bounded. So u is equal to I can take r minus a. So r minus a, it is also, so this is a straight line, this is the point, this is called minus infinity to 2 comma a, and this is a union of a comma infinity. So x is connected, then u is connected, u is not connected. This happened that u is not connected because we can get two disjoint set. So another factor is x by u is compact, then x is compact. X by u equals to r by r minus a r minus a, we can get a is a compact, friends, but x by x. So if x is compact, then u is compact. This is not possible because x equals to 0 comma 1, this is compact, bounded and closed, but u is equal to 0 comma 1, this is not bounded. So x is compact, then u is compact, this is not possible. And x by u is compact, x by u is compact, but then x is compact. No, because you will see that r minus a equals to a, this is compact, this is compact, but x equals to, in here x equals to r, then it is not compact. So x by u is compact, but then x is not compact. Number D is correct. If x is compact, then x by u is connected. Number D, option D is correct. Number 8. Let A be a non-empty subset of a topological space X. Which of the following statement is true? First result is that important result, A is connected, that implies A bar is connected. A is connected, then A bar is connected. A is path connected, that implies A bar is path connected. Example, x sine 1 by x belongs to R, subset of R, where A bar is connected, that does not equals to path connected, PC, path connected. So this is not possible. A is connected, then its closure is connected. This is not possible. If A is path connected, then its closure is path connected. This is not possible. And if A is connected, then its interior is not necessarily connected. So it is not possible. Example, if you see x sine x 1 by x is the given example. So if A is connected, then its interior is not necessarily connected. This is correct. And if A is path connected, then its interior is connected. This is not possible. Number 9. Consider the set x is equal to minus infinity to 0 and 1 by n with the topology, then 0 is a isolated point. Answer is 0 is a limit point, it is not isolated, limit point of a subset 1 by n, and minus 2 comma 0 is an open set, and minus 2 comma 0 is an open set. This is also, this 2 answer is correct, another 2 is wrong. X equals to minus infinity to 0 and union 1 by n such that n belongs to capital R, and this is the line. You will see that this is 0 to minus infinity, and this point is, and this point, this is the limit point, friends. And another point is 1 by 3, 1 by 2 and 1, and this is x. So whatever we see that minus 2 comma 0, this is the minus 2 comma 0, minus 2 comma 0 point is open set. Open set, open to open set to R, open set of x, and 0 is a limit point, and 0 is limit point is 0 of the subset. This 0 is an isolated point. This is not true. Thanks for watching.